interesting point made earlier about CubeSats not being that interesting. I hope to blow that preconception out the water. And there is a bit of a outlandish claim here, the most advanced CubeSat in the solar system. We can blame the good Dr. Susan Jason for that. She egged me on to put that claim in. I hope by the end of this presentation, I hope that you'll agree with me that that probably is the case. So we do have a Facebook page, www.facebook.com/nanosats. I would strongly recommend you to go check that out. We are, not to steal the thunder of later on through the presentation, but we do have quite an interesting site happening there on Monday. And of course, we've got a Surrey Nanosats Twitter account as well. So what I'm going to go through the history of the STRaND program. It's very new, so it's a very one-slide type thing, and the philosophy of the STRaND program. Then I'll go into the system overview of STRaND 1. Then I'll pick out some highlights of some of the subsystems that are quite interesting. Then I'll go through the ConOps and some of the highlights of our planned mission. And then I'll go on to the future. This is quite an ambitious program. So, it all started one February morning. It was quite dim, it was raining, you know, it's cold in February. My boss comes in and says, "Shaun, wouldn't it be great if someone put a mobile phone into space? Go off and do something with it." Well, okay. So in April, we had a feasibility study, internally funded, and we looked at putting a mobile phone onto a 3-unit CubeSat, and I'll go into the reasons why we're doing that later on. In June 2010, we managed to kick off the mission full bore, as it were. In December 2010, we started getting our first hardware in. In January 2011, we had our first press release. You may have heard about that. It did catch Jonathan Amos's eye. And in summer, so about now, we've had our CDR, and we're just starting AIT. So we're starting to cobble it together, program some of the controllers, making sure all of the subsystems talk to each other properly. Hopefully, by December 2011, we'll be ready for a launch. We're looking at a launch in the first quarter of 2012, but it's not sorted yet. So the philosophy of the STRaND program. STRaND actually stands for Surrey Training, Research and Nanosatellite Demonstrator, or demonstration. The D's not important that much. It's basically for brave or foolhardy volunteers. If you ask my wife, she'll say foolhardy. If you ask me, I'll say brave. It's Surrey. When I say Surrey, I mean the University of Surrey, and I mean SSTL combined. We're working on this together, and we're all doing it in our free time. The academics at the SSC are doing it in their free time. They don't get paid to do this. I don't get paid to do this. This is in our lunch times, in the evenings, and at weekends. So I'm sure all of you know plenty about doing that. It's about taking more risks and learning more from taking those risks and learning it quickly. So it's about turning things around really quickly. Oh, that doesn't work, we'll try it another way. That doesn't work, let's try it this way. It works. One of the best ways to encapsulate the philosophy would be to try and be more ambitious for less money. One of the things Doug did tell me when I started this program was it's okay to fail. He's got it in his head that this is like a DARPA type thing, so it's okay to take the risks. If it fails, okay, that's not so good, but you've learned a huge amount out of it. And SSTL gets a great amount of capability from getting these engineers trained up with such a fast mission, and it actually helps the corporate side of SSTL by getting all of this experience into an engineer so quickly. It keeps the informal ties with the SSC. If you haven't seen it already, we've got a lovely new integration facility, but it does mean we've moved completely out of the university campus now. So it's a way of keeping those ties, because at the end of the day, we were born from the Surrey Space Centre. We do see it as our innovation centre. It's the real drive for a lot of our cool kit. And we want to keep STRaND as a way of trying out that cool kit. STRaND 1, we hope, will be the beginning of a very long line of STRaNDs. So it's trying to keep it sustainable. So our first concepts for STRaND 1, we were basically looking at a 3U CubeSat and how you can arrange it in different ways. So these are just some of the arrangements we looked at, trying to make sure that it was going to be, we were going to get enough power regardless of if it was tumbling or if it was 3-axis stabilized or whatever. We actually settled on that bottom right corner arrangement. So we have deployable panels, but before those panels are deployed, it can be in a tumble and still be power safe. So we looked at developing that concept, and we're at a stage now where we've got some fairly detailed CAD models and actually some production. Now this is the system. I've tried to move away from the actual block diagram type things. This shows the system in a really neat way because it treats the mobile phone as a separate entity. And indeed it is. I mean, although it's inside the CubeSat structure, logically it's a very separate entity. So we've got only these 3 interfaces between the two. So the CubeSat is very much a classical CubeSat, although very, very advanced. We've got 3-axis stabilization. We've got 2 sets of propulsion technologies. We've got a traditional butane type thruster. We've also got another thruster called a PPT. I'll go into that in a bit more detail later on. We've also got optical payloads. We've got magnetometers, very traditional things, but the fact of cramming all of this into a 3-unit CubeSat is quite new. One thing I should mention really is the Wi-Fi. We are looking at doing a Wi-Fi intra-satellite link between one of the boards inside the CubeSat and the mobile phone, which means we don't have to worry about antennas on anything because it's just, it's that far. So this is the most detailed and the most up-to-date design we've got so far. As you can see, I've put the arrows on there to give you a sense of the orientation of what it will be like in flight. The white patch antenna at the back is a GPS antenna. The 2 deployable panels are made out of carbon fibre. All of the cells are triple junction M-core cells that fell off the back of a lorry. The PCB at the top there, we're going to do an experiment on that and directly bonding the cells to the PCB. And instead of wiring those cells separately with its own wire, the tracks on the PCB will actually take the power. So that will be an interesting experiment. The dark circle at the top there is actually a sun sensor, so that's a 180-degree field of view webcam, basically, with some clever software behind it that constantly looks for the sun. And then at the front here, you can see our 2 antennas. I'll speak about those in much more detail later on. So if we start stripping away some of the things, you can see it's just a traditional CubeSat avionics stack at the front, but at the back we've got this what we call a cargo bay or a payload bay, and that's a separate aluminium box in itself, and we can put any payload in there. In this case it's the mobile phone is in there, and we can integrate that separately and slot that into the CubeSat when it comes to final integration. So that just shows you the antenna in a bit more detail. At the front here you can see this strange spiral type arrangement. This is what we call PPTs, pulse plasma thrusters, and it's basically a form of electric propulsion where you cause an electric arc discharge at the back of the thruster, and it ablates a very small amount of the electrodes as that discharge takes place. And because you've got the discharge, you've also got a J cross B field, so you've got an electric field interacting with a magnetic field, and because of this ablated material from the electrodes ionizes, you actually get a small puff of plasma which then gets accelerated out of the thruster. And I'll explain the arrangement later on, but we've got them in very distinct units in the structure. And that's just one of the pulse plasma thrusters in a bit more detail. You can see it's got 2 very long electrodes and quite a large capacitor at the back. We've gone for a traditional CubeSat type solution in that we've gone straight to cloud space to get our power system. this isn't to say anything against SSTL Power. They're just snowed under at the moment, and no one had any time, even free time, to build our own. So we took a lot of pragmatic decisions very early on as to what we were going to build ourselves and what we were going to buy in. And going into the payload bay, you can just catch a glimpse of the mobile phone there. But also, we've got our reaction wheels in there. And we've also got some magnetorquers. We've also got the GPS board. And we've also got a very high performance computer unit there. And that's the one that interfaces with the mobile phone. So that's actually got a Wi-Fi chip on there. It's got an ARM7 processor on there. It's got USB hosting. It's got Ethernet connections on there. We're not using those, but it's there. And that's actually a COTS unit as well. So that's the high-performance board in a bit more detail. The phone we're using is actually quite an old one now. It's a Google Nexus 1. And that was actually... that actually came out in early 2010. And when we talk to Google now, they just don't want to hear about it. This is old news for them. And it was released in 2010, and it's old news. This PCB at the bottom is actually on the underside, and that's another set of solar cells, which of course you can't see because they're underneath. And that gives us the power safety if it's in tumble mode. You can also see there's an aluminium hood, and that aligns with the camera that's on the phone so that we minimise the glare from the sun. But the camera on the phone is actually HD, 720 HD, I'll admit, but we can get HD video and downlink that from the phone, unfortunately not in real time. And then this back plate here is the back of the traditional butane thruster. So there is just it's a hollow cylinder, and that's where we hold our butane propellant. And then behind that is a small resistor jet. So that's just a cut through, pretty picture to split up the presentation. So the pulse plasma thrusters, we've actually got 8 of them on this satellite. Bearing in mind this satellite is a foot long, we've got 9 thrusters, so 8 pulse plasma thrusters and then the resistor jet as well. The pulse plasma thrusters on their own give us 5 degrees of freedom in manoeuvring, and these are electric propulsion, so they're incredibly high efficiency. They'll give us roll, pitch and yaw control, and they'll also give us translational control in the Y and Z directions as well. So this middle unit is the capacitor bank. That draws 5 watts at 3.3 volts, and after that's charged up, it will then give us a lovely discharge of 700 volts for about a millisecond, maybe a bit less. So we've got a very lovely 700 volt line, or many of them actually, between that capacitor bank and all of those pulse plasma thrusters. Very interesting when you start discharging and then looking at the radio discharges as well. That's the butane thruster in a bit more detail. As you can see, it's actually an embedded system, so the thruster is embedded into the propellant tank. It's the only way we can fit it all in the volume allowed. This is an interesting unit. This is our attitude determination unit. You saw one of these cameras earlier. So we've got 180-degree field of view on the top and bottom faces. So one of those cameras is a sun sensor, the other is an Earth horizon sensor, and they both plug into this single unit, and that gives us that basically gives us 2 vectors in the satellite frame, and it tells us at any given time where the sun is and where the centre of the Earth is, and that's great for our attitude determination. And this unit has actually been developed by Hermann Stein at the University of Stellenbosch. Our attitude actuators, it's not often you see a CubeSat that's 3-axis stabilised. This is actually a very rare thing, and you can see actually how much of a nightmare it's been to cram it all in, but we have managed to do so, and we think we've got a design here that will work quite well. As you can see, our magnetorquers are aligned in a T-bone shape so that you don't get any magnetic circuits. And you can see our nano wheels are actually all tried to be bundled into this bottom right corner. That's to keep them as close to the centre of mass as possible. And you can see it does take up some of the volume inside the payload bay. One of the things I will point out is this is another webcam here that's actually pointing to the mobile phone screen, so that we can actually take pictures of the screen of the mobile phone inside the satellite, which we think will be great for getting kids excited in space, especially when we start overlaying stuff. If we've got because the camera on the phone is pointing outwards into space, nominally towards the Earth, so that we'll catch the limb of the Earth with this 5-megapixel camera. But because we can then display that on the screen, we can then start overlaying graphics onto that. So maybe we could put a small UFO and fly that around space on the video, and then record that through that other webcam and then downlink it. So the world is our oyster in terms of capability for what we can do with the imagery we get. Now, this is probably where you guys might be a bit more interested. This is our radio system. We're developing this in-house. You probably wouldn't expect anything less from Surrey, a company that's built by radio engineers. So we've just put in the application for a 2-meter band up link to the satellite at 9K6, an FSK modulation. We're looking at the 70 centimeter downlink. This gives us a bit more flexibility in our data rates. We're hoping to do a 19K2 downlink because, of course, we've got this HD capability. We want to, downlink this in one pass. I've put hopefully because we haven't had any official notification that that's been approved by the IARU, but fingers crossed, and I think we've got a good case for that. In terms of the protocols, we're using just plain old AX25. We want to make sure that the AMSAT community can download our data. There's no point making a really cool satellite if no one's going to download the data and look at it. So we're using AX25. One of the engineers has developed a nano Saratoga, so it's basically a subset of the Saratoga. Lloyd, please don't ask me questions about that. I don't know anything. And we are looking at maybe doing a CCSDS experiment as well, and I'll go into a bit more detail about that later. We've got a CW mode, of course. It's much lower power than when we're pumping out the data. If we get into a spot of bother, we'll resort to this CW mode and use Morse code to give us some key telemetry points. It's a modular design in the radio system. The intent was that we can use the same digital back-end if we want to do a STRaND 2 and go up to S-band. And so that it's actually broken out into 2 boards, and I'll show that later on. It actually shares some design components with future SSTL designs. We're basically using this as an opportunity to try out some chips before we fly them on SSTL missions. And of course, we're using the University of Surrey as our ground station, because they've already got the infrastructure set up. So we've got 2 boards. We've got the digiboard and the analog board. One thing that's quite important is these 2 chips do actually act as transceivers. They can work in a transmit mode or in a receive mode. At the moment, we're dedicating one to receive and one to transmit. But for any future mission, we can actually change this interface here for a cross-strapped interface, and that would then give us some dual redundancy. We're using a PIC24 microcontroller, and the rest of the satellite bus is on I2C, so the PIC24 has an I2C node on it. It would be very easy to turn that into a CAN node if we wanted to fly it on a traditional SSTL setup. This is just to show you how far along in the design we are. The actual physical design of the antenna deployment has reached a stage where we're trying to build some prototypes. We're actually going to get those 3D printed because that's a new manufacturing technique we're quite interested in. The digiboard is in the very late phases of ECAD. It's pretty much routed. There's just 1 or 2 lines left to route. And the RF front end, we've got breadboards that show it works. Now, the mobile phone itself is incredibly capable. This is the main reason we want to fly it on the phone, on the satellite, is because it's got a lot of capability that satellites need to have. It's got a processor, it's got a radio system, it's got data storage, it's got a magnetometer so that it can detect the Earth's magnetic field, it's got batteries, so it's almost a satellite in its own right. We're flying it as is. We're not going to take it apart like we've got down here. That's just to show you how small the electronics bit is compared to the rest of the satellite, the rest of the mobile phone unit. The one thing that we are messing around with is the operating system. Of course, it's an Android operating system, which means it's open source, which means we don't get sued if we start tweaking around with it. And we're only very slightly tweaking it so that we can deal with the inputs and the outputs a bit more easily. Just to drive the point home, that mobile phone has got an ARM9 processor that can do 30 million floating point operations a second. That's 3 times quicker than a Cray supercomputer in 1969. Something that I can put in my pocket is 3 times quicker than what the Cray company could do back in the 70s. I think that's an important point, and it's more important a point that we can put that on a satellite today. And this probably doesn't show up very well, I do apologise, but this is basically our deployment mechanism. We did look at buying in what's known as a P-pod, so it's the box that deploys your CubeSat from the rocket. They have to be self-contained so that if your satellite falls apart, it doesn't ruin everyone's day. But the P-pod that's built in America is actually quite expensive, and it's actually quite heavy as well. It's a solid block of aluminium, and so we decided that we were going to try and design our own. So this is the S-pod. It's got a cylindrical cross-section rather than a square one, and it's actually made out of carbon fibre, so it's incredibly light. It's actually very, very easy to build, of course, because it's a cylinder, which means you just get a rather large pipe and you just wrap your carbon fibre around it and cure it that way. This is a preliminary concept. The CubeSat doesn't look like that anymore, unfortunately. But I'll talk about this in a bit more detail later. So for low Earth, for launch and LEOP, the very first thing up once we've deployed from the rocket, of course, is we'll deploy our antennas. That'll actually be set on a delay so that not even the OBC has to be switched on. That's controlled directly from that PIC that's on the radio board. It'll just realise, oh, I've switched on. It'll wait maybe a minute, and then it'll blow the resistors that are holding the antennas down so that our antennas deploy almost immediately. Once we pick up the CW beacon, that's where we define mission success. So we've got the bar really quite low, but you know, most of the team are graduates, so we wanted to set that bar really low just so that we could say we've got mission success. Then we go into do our detumble phase, where we're using the CubeSense board that I pointed out earlier. We've got incredible data sets because we've got 2 magnetometers. We've got the one that's on the OBC. We've also got the one that's on the mobile phone. We've got those 2 wide-angle cameras. So we think we've got enough data to try and detumble very, very, very quickly, especially because we've got the reaction wheels as well. We're trying to detumble within 24 hours. As you can see there, we've scheduled ourselves a week. So, you know, we aim for the moon and maybe you'll get into space type philosophy there. And then after we're settled, after we're out of our Y-Thompson, after we're 3-axis stabilized, then we'll deploy our carbon fiber panels and start to get some real juice into the system. Then, depending on how long we've taken, we'll try and do an inspection mission. Because we've got these propulsion systems on board, we'll actually want to try and fly quite closely to something else that's nearby. So it might be a rocket body, it might be another CubeSat that deployed from the same launch. And what we want to do is fly quite close to it and take pictures of it with the mobile phone. It's highly dependent on, firstly, how long we've taken to detumble, because that then is a function of how far we would have drifted away from whatever we want to fly close to. And we've only got 2 meters per second delta V. It's also dependent on the difference in the ballistic coefficients. If we're flying with another CubeSat, then the ballistic coefficients are quite different, quite similar, which means the drag will be quite similar, which means we'll both be slowing down at the same rate. If we're trying to catch up with an empty rocket that's huge and mostly hollow, that's going to drop much quicker than we are. So we'll have to, that would then have a much greater requirement on our propulsion system. Maybe we only get one shot to fly close to it, take a few pictures, and then it drops away. We're making great use of the Surrey Space Centre Astrodynamics group. Dr. Phil Palmer, of course, is renowned in this sort of field for the theory that goes with formation flying, and we're tapping him and his team very much to, to see how we can optimise this part of the concept of operations. But you never know, we may not be able to do this at all. It all comes down to how far away we are from anything of interest. Then once we're all settled, then we'll start getting into our experiments. So first thing we want to do is to use some traditional SSTL software and see if it'll actually run on a COTS OBC that we're just buying in. Then of course we want to see if the mobile phone does actually work in space. So do the accelerometers give us any useful information? Does the flash memory completely die every time you fly through the South Atlantic anomaly? Probably will, but can we recover from that? Then we'll do some Android software experiments. Can we? Oh, blimey, that went quick. Yeah, can we do some software experiments? Android actually flies Java, so we've got the opportunity here to do some really high-level, really intelligent software on the phone. Radiation effects on a capacitive touchscreen. You've basically got a very large area capacitive sensor that's going to be hit by charged particles. And because those charged particles are hitting it randomly, maybe you can randomly generate numbers from that. There's a few chuckles there. Be interesting to see what the UCube talk says tomorrow. And of course, outreach. We've got a mobile phone on there. How cool is that? At least the kids will think that. And what we really want to do is try and get kids to realise that there's a lot of cross-pollination in the different electronic fields. You can just design a wireless router for your home, but maybe you might be interested in space. The physics isn't different, and space is way cooler, to be honest. Obviously, we want to download images. You've got a 5-megapixel camera there. We may have a 19K2 downlink. There's plenty of scope for just bringing out your FunCube dongle, listening to STRaND, and getting a very nice picture. But, we are a bunch of graduates. We don't know how to do outreach like you guys do. And please take this as a serious request. We would love you guys to get involved. Tell us how we could make the most of this satellite. Tell us how we can take it to schools and really get some people enthused about space. So by all means, please come call me afterwards and we can have a chat about that. So just go through the budgets very quickly. We're a little bit over the CubeSat standard of 4 kilograms. We may be able to get that under, but I doubt it. Orbit average power, we're looking at 2.7 watts. That's about normal for a CubeSat. If we go into an inertially fixed mode, so actually stare the solar panels at the sun instead of following the Earth's sphere, we can get that up to 5 watts. When we're tumbling and we haven't deployed the panels, we're at 1.5 watts, which is still plenty for doing radio experiments. The uplink, of course, has got a ridiculous margin on it, and the downlink is not too shabby anyway. So I've already spoken about some of this stuff. These are just the phone experiments. So we can do all of this just on one unit. Things like Java agent processing, getting apps to talk to each other within the phone. You basically start developing a software ecosystem within the processor, and how do all of those different apps react when they talk together. It's just an idea of what we could do. What we actually want to do is something a bit more interesting, and an inter-satellite link experiment. This does require us to fly with another satellite. NASA are interestingly doing a very similar mission called PhoneSat, and they're actually going to launch before us, I hate to say, but you know, they do have plans to keep their program going as well, and so we would really like to fly with their PhoneSat 2, or maybe we just strap another mobile phone to a couple of batteries and a couple of single junction cells, fly that in a one-unit CubeSat structure and call that STRaND 1A, and then we can start doing some Wi-Fi inter-satellite links with that. Yeah, and it would just be a proof of concept, transfer an image, maybe that sort of basic stuff. If it works really well, then maybe we could do something a bit more technically challenging and start getting the two apps on two different phones to start talking to each other, working cooperatively, maybe even doing some distributed processing. Now, this is something I really want to do on STRaND, and I think this will be great for outreach, is a chatbot. Now, a chatbot is actually it's basically an artificial intelligence that runs in Java, and that would run on the phone inside STRaND. But because it's an artificial intelligence, you can talk to it. So imagine being able to send up your AX25 protocol text message and actually talk to the satellite, not talk to someone else through the satellite, talk to the satellite itself. So you can, in natural English language, so you would say to it, you know, how are you? And then the software would look at some of its telemetry points, turn that into a natural English language response, and send that back down to you. And there are examples of this online already, and I'll just show you one, because this is actually existing software, and it's open source, and it's in Java, so it's all fine. So I can type here, hello James, and I get a response from a computer that's somewhere off in the internet.
Hello there. Lieutenant. No. Lieutenant.
That's enough of him. Right, this is really important. If Graham cuts me off, this is the one thing I do want to actually talk about. How do I get this back? There we go, that one. We're going to run a Facebook competition from Monday. I've already shown you some ideas of what we could do in terms of software experiments on the phone, but we do truly think that the possibilities are endless, and we want to get the UK's public to come up with ideas. We'll pick the 4 best ideas. If we think you can write the app in a couple of months, then you've got the chance to fly your own written app on our phone in space. You'll get one orbit, and you can do whatever you like. So please, 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 please check out Facebook. Check out the NanoSats Facebook page. Tell your friends. Have a think. Maybe your app could fly on our satellite. And that comes out on Monday. So obviously, SSTL is no longer a university-type organisation. We are cold-blooded and corporate and cutthroat. We do want to try and make some money out of the technology we're developing on STRaND. We think the pulse plasma thrusters could be quite interesting. Do you guys think they're interesting? Do you think a CubeSat transceiver built in the UK, designed and built in the UK, is an interesting thing? I'll be really interested to hear your feedback at the end of this. Of course, we've got a CubeSat resistor jet design out of this. Do you think that's interesting? Do you think the attitude actuators are interesting? We think the S-Pod is quite an interesting one because it's a much lower mass CubeSat dispenser than anything that's out there in the market already. And of course, it's starting to get CubeSat development experience into SSTL, and so we can actually address that bottom end of the market. And who knows, if these mobile phone components work, maybe you'll see them working their way into SSTL satellites and bringing down the cost of SSTL satellites. We have got some funded studies at the moment from the Technology Strategy Board. One of them is looking at incorporating CubeSat technology into traditional SSTL satellites. That's going on really well. There's another TSB feasibility study looking at using the Android software on a more, what I'd call traditional satellite processor, the PowerPC 750. And we've also got another study looking at deploying CubeSats from larger satellites. This would then enable us to broker launches for CubeSats without actually having to get launch agencies involved, because you would actually be classed as part of a larger satellite. And from the discussions we've had with other universities who are doing CubeSats, launch is a big, big problem. And if we can help solve that, great. And of course, we're looking at STRaND 2 now. STRaND 1 is getting to the point where we'll be ready for launch in half a year. We want to do more. As previously mentioned, you're always looking to do something better. So if we can get STRaND 2, that cements us as a sustainable program within Surrey. Always the University of Surrey and the SSTL people talking together, which is great for both organisations. And there's plenty of cool technology out there that's still being developed. There's plenty of stuff that always comes onto the market every year. Let's try and fly it in space. Let's see if it works. And also the University of Surrey is always developing new gadgets, new payloads. And we think this gives them an opportunity to get them into space and to actually try them out. And actually, I think it would be great to try and get AMSAT-UK involved in the STRaND programme in a more sustainable basis, in a more formal way. Please come talk to me after the presentation. Before I do actually finish off properly, I just want to say that this is the first CubeSat with an electric propulsion manoeuvring system on it. It's the first CubeSat that can rival supercomputers. It's the first CubeSat with 2 separate propulsion systems on it, and it's being built within a 2-year program by kids in their free time. And if that isn't the most advanced CubeSat in the solar system, well, blow me.